Google just released the largest openly available language model trained with provable differential privacy. Here's what that actually means. Today, we dissect VaultGemma, a 1 billion parameter language model trained end-to-end with differential privacy. That combination is rare. Open weights plus formal privacy math. I'll walk you from the headline facts to the engineering choices, show the trade-offs, and give practical steps to try it. By the end, you'll know when a private model is the right tool and when it isn't, plus how to experiment safely. First, the headline numbers. VaultGemma has 1 billion parameters and was trained on roughly 13 trillion tokens. Google reports a sequence-level privacy guarantee of epsilon 2 and delta 1.1 times 10 to the minus 10. Those numbers come from training with DPSGD, which clips gradients and injects Gaussian noise. Open weights mean you can download the model and inspect it yourself, so anyone can validate claims and run experiments. Why should privacy guarantees matter to you or your company? Models trained on web data can memorize rare strings like emails or API keys. Attackers craft prompts that coax those strings back out. VaultGemma aims to stop that memorization at the training level, which reduces the risk of sensitive data leakage. That changes the threat model for regulated deployments, but it also introduces performance trade-offs we'll examine next. Let's explain differential privacy with a concrete metaphor. Imagine a photographer capturing a crowd for a city study. Instead of watermarking faces, she blurs each face a bit and mixes in random pixels. The photo still shows crowd patterns, but individual faces are obscured. DP does the same during training. Clip each example's influence, then add noise. That math delivers bounds, epsilon and delta, on how much a single sequence can affect outputs. Now the mechanics. DPSGD. During each gradient update, the training pipeline limits each example's gradient magnitude with clipping. Then it adds calibrated Gaussian noise to the sum. That noise protects individual examples across many updates. The trade-off is direct. More noise or tighter clipping means stronger privacy but lower accuracy. Google balanced that trade and reported sequence-level epsilon 2, which is stringent for long textual sequences. But how did they scale this to 1 billion parameters? Scaling DP training is non-trivial. VaultGemma ran on a 2048-chip TPU v6e cluster to move through 13 trillion tokens efficiently. The team developed new scaling laws to predict utility at a given privacy budget. Old rules of thumb for non-private models break under DP because noise and clipping change how compute converts into performance. These new scaling laws are practical. They suggest batch sizes, clipping thresholds, and training lengths that actually yield usable private models. What about raw performance? VaultGemma lags similar non-private models on standard benchmarks. For example, on ArcC, it scores about 26.45 versus 38.31 for a non-private 1 billion parameter model. Google summarizes the gap as roughly 5 years of progress behind the latest non-private models. That sounds big, but the model still handles many real tasks. So where does it shine despite lower benchmark numbers? VaultGemma shines in risk-sensitive settings. Imagine a hospital prototype assistant summarizing clinical notes without risking patient identifiers leaking, or an internal legal assistant that drafts memos from proprietary documents. In those workflows, avoiding memorization can be worth sacrificing top leaderboard scores. The model's 1 billion parameter size also makes it economical to run and iterate locally. But remember, DP protects training data, not your inference inputs, which means operational controls still matter. A critical point: fine-tuning can erase the privacy guarantees if done improperly. If you fine-tune VaultGemma with vanilla SGD, you can reintroduce memorization. To preserve privacy, use DP-aware optimizers like Opacus for PyTorch or TensorFlow privacy. Track your epsilon and delta during the entire fine-tuning run. Use larger batch sizes where possible, and pilot different clipping and noise schedules. Want to keep guarantees end-to-end? You need DP across both pre-training and any adaptation steps. Here's a hands-on starter path. First, read the model card to understand license and limitations. Then download weights from the public repo and run local inference on non-sensitive benchmarks. Use the provided transformer snippet to avoid typo issues. Evaluate with your own metrics before touching private data. If you proceed to fine-tune, set up a DP-SGD pipeline and simulate privacy accounting. Those steps protect your legal and compliance posture, but there's one more governance detail to check next. Compliance teams love concrete artifacts. VaultGemma supplies documented privacy parameters and a public training methodology. That helps with GDPR risk assessments and EU AI Act compliance because you can point to an epsilon and delta and an explicit DP-SGD recipe. Still, a documentation pack doesn't replace a formal legal or risk review. Expect auditors to probe dataset curation, downstream risk, and inference controls. Next, we'll examine limitations that compliance teams should flag. A mid-video recap. VaultGemma is an open-weight, 1 billion parameter LLM trained with DP-SGD, reporting epsilon 2 and delta 1.1e-10. It trades some accuracy for provable privacy and offers practical scaling laws and recipes. You can download weights and experiment, but fine-tuning requires DP tooling. What we haven't covered in detail yet are the engineering knobs and the unseen risks, which come next. Privacy accounting is subtle. Each training step consumes a bit of the privacy budget. Repeated updates accumulate epsilon. Sequence-level accounting treats entire documents as the unit of protection, which aligns with real text. If you chain multiple DP trainings, you must compose budgets across runs. Tools exist to compute composition, but they require precise logging of batching and sampling rates. Mess this up and your claimed epsilon is wrong, which could harm both privacy and compliance. Quality versus privacy trade-offs are concrete. Think of privacy like adding blur to a photo. Increase blur and you preserve anonymity, but lose detail. VaultGemma finds a balance that keeps the image useful for many tasks, but not for the most demanding reasoning benchmarks. For teams that need sharper answers, private models will need more capacity or smarter noise schedules. The research direction is about recovering that lost detail while keeping provable guarantees. The release also moves research forward. Open weights let labs reproduce results and build stricter privacy benchmarks. Expect new memorization tests, shared evaluability-driven improvements to noise schedules. That scrutiny accelerates progress because researchers can run apples-to-apples comparisons. Open models become a common ground for policy conversations too, but community scrutiny often reveals unexpected failure modes we should watch for next. Watch for these failure modes: dataset contamination, miscomputed privacy budgets, and leaking via downstream retrieval. Dataset contamination happens when private strings appear in the validation set, skewing memorization checks. Miscomputed budgets come from incorrect sampling assumptions. And leaking via retrieval is a runtime problem. Even a private base model can repeat private input it was given at inference time. Mitigations include strict dataset hygiene and layered runtime protections. What about languages beyond English? VaultGemma is English-heavy, and multilingual DP training at scale remains a frontier. Non-English datasets often have different token distributions and rarer sequences, which complicate clipping and noise tuning. Building private models for clinical or legal languages will require domain-specific recipes and careful curation. Expect more releases that tackle additional languages and specialized corpora, but that work will take time and careful engineering. If you plan to adopt VaultGemma in production, protect the inference pipeline. Differential privacy shields training data, not user prompts. Use input redaction, enforce access controls, encrypt data in transit and at rest, and log queries for audit. Combine retrieval-augmented systems with safeguards so your retrieval layer doesn't pull sensitive snippets into prompts. Follow defense in depth. DP at training is one layer among many required for safe deployment. Let's talk licensing and openness. VaultGemma's weights are public on model hubs, but usage depends on the model card license. Read the terms before deploying commercially. Open weights enable reproducibility and auditing, yet responsible use still requires internal policies. For many teams, the sweet spot is using the model for prototypes and benchmarks, then investing in DP fine-tuning with legal oversight if moving to production. What comes next in the field? Expect larger DP models, adaptive clipping methods, and private RLHF workflows that keep the entire loop differentially private. Researchers will push to recover utility while maintaining epsilon and delta budgets. Policy groups will use releases like this to ground regulations in concrete examples. The next breakthroughs may make private models match non-private peers on many tasks. But that future depends on both compute and clever math. Back to you. How should an engineer start experimenting? Clone the model card, run local inference on public benchmarks, then design pilot fine-tuning runs with DP toolkits. Log sampling rates and batch sizes precisely for privacy accounting. Start with non-sensitive datasets and move to private data only after successful pilots and legal sign-off. This disciplined path keeps your privacy claims credible and your project auditable. And there's one final strategic idea to consider. Strategically, open private models lower the barrier for standards and audits. If your organization values provable privacy, contributing to benchmarks and publishing audits helps raise the industry floor. Small companies can now prototype private assistants without building DP from scratch. That capability changes procurement and risk decisions across sectors, and it creates pressure for transparent certification processes. So what should your next move be? Quick final recap. VaultGemma is an open-weight, 1 billion parameter model trained with DP-SGD, offering sequence-level epsilon 2 privacy. It trades some accuracy for provable protection and provides practical recipes and scaling laws. Use it for regulated prototypes, research, or safe internal tools, but keep inference protections and careful fine-tuning practices. If you want to dig deeper, grab the model card and technical report, and run small pilots before any production rollout. One last thought. Privacy in AI is a systems problem, not a checkbox. VaultGemma is a major milestone because it proves large-scale DP training can be practical and open. But safe AI requires design across data, model, and deployment stacks. If your team treats DP as an add-on, you'll miss critical risks. Treat it as a first-class design constraint, and you'll build systems that regulators and users can trust, starting with deliberate experiments like this. If this helped, like and subscribe for deep yet practical AI explainers. Tell us in the comments what you'd test first with a private model like VaultGemma.